If you look very closely at this machine, you will note that there is a giant gaping hole in the column and there is a matching one in the base. And if we don't do anything about that, they are both just going to fill up with chips when we use the machine. So today we are going to make some way covers and we're going to try 3D printing them. Is that a good idea? Of course it is. Maybe. Welcome back to Cloud42. I'm James. A few weeks ago, I saw a YouTube video from Functional Print Friday showing a technique for printing collapsible bellows out of TPU with PLA support. I'll put a link to that video down in the description and up here, and I highly recommend you go check that out. In that video, he shows this technique for stacking up layers of PLA and TPU so that it forms a three-dimensional pleated bellow that can expand and compress once it's printed and all the support material is removed. And I thought that seemed like the perfect solution to make way covers for a machine tool like this one, which needs way covers. So I thought I would give it a try. I've got all kinds of open questions. Can we make them so that they're long enough? Will they support their own weight? Will they be durable enough? Will they actually survive exposure to chips? I don't know, but I know how to find out. Let's give it a try. Now, this machine actually did come with way covers for the back of the Y and the Z axes, but I don't like them. This is what the machine came with. It came with this sheet of rubber. It attaches to the back of the table down here, and it attaches to the slide for the Z axis up here at the top. So when the table's all the way forward and the head is all the way up, it kind of just hangs in here, and it prevents chips from getting into the column and into the ways as long as they're just flying straight. They'll fly, they'll either hit this or they'll go beside it. But it doesn't really protect it, it just kind of hangs in front of it. So it doesn't enclose the space, so if you've got mist coolant or compressed air blowing things around, especially in an enclosure, those chips are going to go around the sides of this and find their way into it. They're also going to end up on the flat ways of the Y surface here, and that's a bearing surface. And so even over on my knee mill that has a similar kind of cover like this, even without compressed air, all kinds of grit does end up down there. So I really would like something that provides a little bit more containment, like some bellows that actually go over the ways and completely enclose them, not just from the top, but also from stuff flying in from the sides. The other issue that I have with this style of way cover is that it's essentially uncontrolled. So when the table's all the way forward and the head's all the way up, it's fine. It's not going to get in the way. But when the table's all the way back, like this, and then the head comes down to mill, you can see that that's flopping forward. And unless you do something to control it, it can actually flop over the vise and over into the cutting area. You can see that's actually out far enough that the spindle could impact it. Is that really a problem on a manual machine? No, not really, because as you're moving the machine around, you can see what's happening and you can manage it. But on a CNC machine that is just operating under its own control and moving potentially very quickly, and potentially while you're nearby but not paying total attention to it, this could be a problem. It could get in the way. It can either bunch up behind the setup against the column and cause problems just due to getting pinched, or it could actually get in the way of the work. Or it could even just fold forward and be in the way, depending on where we mount the sensor for the infrared wireless probe. So I don't like this. I want to replace it with some bellows that fit tightly to the machine and collapse in a controlled way. I've already got a 3D scan of this machine, so we don't even need to take any measurements. Let's just go into the computer and see if we can come up with something that'll work. To design the bellows for the Y-axis, I just started by fitting a sketch in the general shape I wanted for the bellows around the Y-axis dovetails. Now in this case, the actual running surfaces are in the center here, and then there's a little lip on the casting, and this is a painted outside wall and a painted surface down below. So I just designed the shape of the bellows to actually sit right on the top, on the non-functional surface of the dovetail way there, and then to hang over the side and to hang down low enough that it completely protected the sides of the dovetails. This flat surface on the bottom here is the actual weight-bearing running surface, and I've got the way cover designed so that it will come down and overlap that, protecting it from the sides. I I did actually dimension this because I do want it to be constant width all the way around, just because of the way this thing is going to be constructed. I just picked a number. I figured 30 millimeters would probably be about enough height. I made the inside radius 10 millimeters and the outside 40. And again, those differ by 30 millimeters so that we have a constant width all the way around. And then to actually design the bellows, I did exactly what's shown in the Functional Print Friday video and created a sketch that has a solid that's interrupted by these slots. So there's a slot coming in from one side, and then there's a slot coming in from the other side, so that in the end, this creates a solid that's kind of a Z-fold structure. There's a seam here, and then the next seam up is on the other side, and then the next seam up is on the other side, and it creates this Z-fold structure that when this is swept out and then printed, this can then expand and pull apart like a bellows, which is exactly what it is. So to actually create that, just use the sweep command, and I just select that contour or that profile and then sweep it around the outside edge of this other sketch, and that creates this three-dimensional structure. And you can see that those slots go all the way through, and you can kind of see the structure of this and imagine what would happen if you grabbed the two sides of this and pulled them apart. Now we can just take this solid and export it and take that directly into the slicer, but there are a couple more things that we'll want to add to it first. For the Z-axis, I used a little bit different technique. I started out the same way with a sketch for the actual shape of the bellows, and in this case I added a little bit more material because it's vertical. I didn't want to let it just hang, so I added more material to make it actually kind of clip around the dovetail. There's some extra space in there so it'll move, freely, but it won't actually pull off. It'll grip around the dovetail and prevent that from happening. And then to model this, instead of doing a full sketch of the full cross section, I tried a little bit different technique, and I just sketched the slots for one set of pleats. Then I extruded the entire block, used the sweep command to cut out one pleat, and then used a pattern to pattern that sweep command down to create multiple pleats for the entire bellows. And the reason I did this is because using the pattern with parameters, so I've set this up with parameters for the thickness of the individual walls, the thickness of the space, the number of pleats. And when you do this and then use these parameters inside a sketch for the patterning, things can get a little bit weird. It seems to be much more reliable in Fusion if you're patterning features in the 3D space and not trying to do the patterning inside the sketch. And so I was just playing around with this, and this technique allows me just to change the patterns and instantly change the length of the actual part without having to go in and fix up things that went wrong in the sketch when I changed the numbers. Of course, to actually attach the bellows to the machine, we're going to need some sheet metal brackets. So I just came in and used the sheet metal tools in Fusion and designed a bracket here that fits on the top of the Z-axis. This uses the existing screw holes that are in the front of the slide. It's got some tabs on the side that are for future use, and then it bends around underneath here and creates a surface that we can screw the bellows to. Now, I don't think the rubber end cap of the bellows is going to be rigid enough, so I also designed a steel plate that's going to go inside of that. And if we look at this in cross-section, you can see that I just hollowed out a space in the end cap, this 5mm thick solid end cap that's printed in the bellows. I just made a pocket to fit that sheet metal part in there, and then we'll use a button head screw from the inside to go through that plate, through the rubber, and into this other sheet metal bracket that's then attached to the machine. There's a corresponding plate on the inside of the bottom of the Z-axis, and that will then attach to a bracket that I designed down here at the bottom. This bracket holds the back of the Y bellows. It just fits into a slot that's hollowed out in the back of the printed part, has screw holes to anchor that to the column using existing holes that are in the machine, and then it's bent 90 degrees to provide a surface to attach the Z bellows. When those come down, they'll just screw into that. And then of course there's another metal plate that fits on the inside of the Y bellows and attaches to the back of the saddle, again using existing screw holes. Now, the easiest way to make all of these sheet metal parts, of course, is SendCutSend, and that's how we're going to do it, just like in other parts of this project. So I'll export those as step files, upload them to SendCutSend, have them bent and powder coated, and for places where we need to actually run screws into them, we can also have PEM nuts inserted. I'll get that done, and then we can just focus on 3D printing the bellows. I'm printing these parts on the Bambu Lab H2D, so I'm doing the slicing here in Bambu Studio, and getting the slicer set up to get exactly what I want was surprisingly subtle. The first issue here is that there is no flat surface on the bottom of this part. This is the Y bellows. There's a step here, so we need to print this all on support, and I decided to just go ahead and print it all on a raft. So in this case, the orange material is the TPU and the red material is the PLA that I'm using for support. So the whole thing's printed on a raft, and then I set the support up to be automatic, and I used the snug style. Set the base and the interface to use the PLA material, the Z distances to 0, and the top interface spacing to 0, just to make sure that we get a good solid and smooth interface surface between them. Now, I do care quite a bit about the direction. What I really want is to have the support material running in this direction 90 degrees to the majority of the part. So we'll finish one layer or one pleat and then lay down the support material 90 degrees to the part, a second layer of support material in the same direction, and then I want the first layer over the support to run 45 degrees one way and the next layer up to go 45 degrees the other way. And this was a little bit difficult because by default, it was trying to do what it calls the bridging layer, which is the first layer over the support, in the long direction, and that left some weird artifacts at the edge of the support. And I really want, since it's 2 layers, I want it to be alternating in 45 degrees. And so I had to come over to the strength tab and change the bridge direction to 45 degrees to make that happen. And with that set, it just sliced, and the automatic supports ended up being exactly what I needed. So I just sent it to the printer and let it print. The Z-axis was, of course, similar, only it's a taller print. And both of these prints took about 20 hours. I think we're showing right now 17 hours and 49 minutes, 18 hours on this one. I think the Z bellows took a little bit longer. And the reason it takes so long is because most of these layers are slow. In the case of the support, the first layer of support is going down over a different material, so it prints that pretty slowly to make sure that it sticks. And then the second layer of support is actually a top layer, so the printer prints that slowly so that it'll have a nice smooth surface. Then when we come back with the next layer of TPU, it's the first layer over support, and so it's going to be printed slowly to make sure that it adheres well. And then the layer on top of that is now a top layer, and so it's printed slowly in order for it to come out nice and smooth. So pretty much the entire print is printed at slow speeds. It takes 20 hours, but this is a case where your patience will be rewarded. As shown in the Functional Print Friday video, these things come out just rock hard, and getting all of the support material out can be a little bit challenging. I ended up using a pick, and I think this is just an O-ring pick that came, I think, from Harbor Freight, and just started working it in and then dragging it through the part to separate it. In the Functional Print Friday video, he showed just pulling it. I didn't find that to work very well. The particular combination of filaments that I was using stuck well enough that I was afraid I was going to damage something if I did that. So I just used a pick, worked it in, drug it through on both sides of the support, and then just very carefully worked all the sheets of support material out. For something this shape, I discovered that it really works best if you work around the entire outside of the part and at least split all of the joints on the outside to give the thing some flexibility so it can move, and then come back, break open all of the joints, at least one side of the support on the inside, and then you have something that's a little bit more flexible. Then you can go back and, run a finger down each side of the support, make sure it's completely separated, and then pull it out with a pair of pliers. And you really have to get it separated all the way down into the root. If you don't, it sticks and it generally breaks when you try to pull it out. And then you've got a mess with little sharp edges, and you will bleed. So use a pick, make sure you get it all separated, and then it comes out pretty easily. And here are the results. I tried a few things. I'll show you what worked and what didn't. Actually, it all worked, but I'll show you the differences. This is all printed in this SaneSmart TPU. This is, I believe, a 95A durometer. So it's got some structure to it, but it's still pretty flexible. And in thin sections, it's quite flexible. So this is the Y Bellows, and this was printed with 0.4 millimeter wall thickness. So there's 2 layers. So as this thing is built up, you're essentially laying down a layer of TPU, then one layer of, a layer of support, and then one layer of TPU and a second layer of TPU before then laying down another layer of support. And so it's pretty thin, but TPU is really tough stuff. So you can see it wrinkles up when I put some pressure on it. It doesn't have a lot of structure. It's pretty soft. And in terms of durability on the machine, my biggest concern would just be hot chips melting through it or chips cutting it. And so I'm not sure that's quite enough structure. One thing that's interesting to note is that because of the shape of this, as you stretch this out, these walls are going to be coming up towards, like in this case, towards the camera, which is going to shorten them. And so, when viewed from this angle, they would get shorter because the angle is changing and coming towards the camera. And so what that means is that this inside radius would have to get larger, or the outside radius would have to get smaller to accommodate that. And really, that's not going to happen. So what's going to happen instead is that additional, you could think of it as tension pulling in this direction, it's going to bend the bellows around. And you can actually see that. If I pull this up towards the camera, you can see that as it stretches, this leg bends in. Now that should be pretty obvious, especially with this thin material. You can see the outside of it there. So definitely, if you're going to design something like this, you need to take that into account. Now, when you buy commercially made bellows from machines, they don't have just a smooth edge like this. They'll have some pleats and some folding in the corner that's designed to provide relief to allow that to happen without that distortion. And maybe that would have been possible here, but that would have then meant for every one of these, you wouldn't just have one layer of support between the pleats, you'd have to have multiple layers to keep them separate. And I wasn't quite sure how that would print, so I decided to just try the simple thing first. I also tried printing this with a 0.6 millimeter wall, and that's what this is. And so it's quite a bit stiffer. I don't know if you can really see that without feeling it, just how much stiffer this is. You can see this is much more relaxed. And this has got a lot more force on it. And that's just because these are 0.6 millimeter thick walls, so 3 layers thick, and you can see they're quite a bit more durable. So I think this is quite a lot more durable. The that effect of them pulling in on themselves is going to be about the same. And kind of what I found is that to get the amount of stretch I needed to cover the distance I needed with the 0.6 millimeter walls, I really needed to have an extra pleat or two to accommodate that. And that's especially true on the Z-axis where the actual extended distance has to be so much longer. So I've got a 0.4 millimeter version here, and you can see this stuff stretches really remarkably well. And because the additional structure here to go around the dovetails, there's a little bit more resistance, but you can see it still does pull in. But I left enough extra space around the dovetail to accommodate that so that it wouldn't jam up over the distance that I actually needed it to stretch. And I did exactly the same thing with the 0.6 millimeter thick walls. You can see there's a lot more force on that. The machine won't care, but I added some extra pleats to accommodate that additional distance. Now, these look fine, but I'm a little concerned about cut resistance. I'm a little bit concerned about heat resistance. We could always throw these on the machine and just see what happens. But I was talking about this in some forums, and I had somebody make a suggestion for a different kind of material entirely. This is probably one of the strangest materials I have ever used. This is called FiberFlex CF, and this is a TPU filament with carbon fiber. Now, does that make any sense? On paper, that sounds pretty weird. Why would you want a flexible material paired with carbon fiber, which typically increases rigidity? It doesn't make a lot of sense, but it does create a material with some very interesting properties. This stuff it's very difficult to describe how this stuff feels. I mean, on the surface, it's just kind of like a TPU that's not very flexible, but it's almost like a fiber material, like a rope or a twine. It's rigid. It almost feels like a heavy waxed twine or something, where it actually will fold with a fairly tight radius, but it just feels like almost spongy. And when you get it extruded and laid out in a thin sheet, it feels almost like a cotton duck, like a heavy waxed canvas kind of a material. And this stuff is pretty tough. Now, technically, I think the carbon fibers in the matrix actually do reduce the tensile strength of it, but you wouldn't know that to play with it and pull on it. The layer bonding is very, very good. And if you use this to print things that are thicker, like rigid parts with thick walls, it ends up being a very rigid kind of a material that is incredibly impact resistant. They also claim that this stuff has a really long fatigue life, which is perfect for the application that I have in mind. So I decided I wanted to try this for these printed bellows, because this just, I mean, we'll see how it stands up in practice, but like if you just take a knife and drag the tip across it, it tends to kind of bounce over the fibers and not really cut into the material like it does in the TPU. So I'm hopeful that this stuff is going to be a lot more durable. Now, that said, it is challenging stuff to print. So this is actually a 90A TPU, so it's relatively soft, but it ends up being much harder even than like a 98 TPU in terms of how it feeds, except that it has some kind of weird compressibility characteristics. So I printed this in the Bambu Lab H2D, didn't really have too much trouble with it as long as you follow the recommendations and bypass the feed path. Now, I have fed it through the buffer, I've fed it in through the four-way adapters, and you can kind of get away with it sometimes. I don't recommend it. The other thing that makes this stuff a little bit difficult to deal with is that it doesn't stick to other materials in the same way you would expect. I tried printing with the same PLA support that worked beautifully on the regular TPU, and it just didn't stick. It kind of mostly stuck, but kind of didn't quite stick. So here's a sheet of the support material that I removed, and you can kind of see the edges are just a little bit ragged. And what happened here is that, this would be laying on top of this TPU, and as this is being laid down, the head would come up, lay the material to the edge, and then as it came back the other direction, it peeled back. So it wouldn't stick at the edge and it kind of curled up. That wouldn't necessarily be a huge problem. It would just be a surface kind of imperfection, except that these layers that we're laying down are so thin that in lots of cases that results in there actually being holes all the way through the bellows, because you're only going to lay down a 0.4 millimeter layer or 2.2 millimeter layers, and as those come over the top, they kind of squeeze around it, the PLA ends up sticking through it, and you end up with a hole all the way through your bellows. So I tried some other things. Another material that supposedly works pretty well and sticks to TPU would be PVA. This is kind of translucent, so it's a little bit hard to see. This is the Bambu Lab PVA. And the main thing that this stuff is great for is that it is water soluble. So you can actually just dissolve the supports. But in this particular case, I have a part like this. It's about 200 grams of material, and it was going to have about 100 grams of PVA support in it. And I did not want to try to dissolve that and then actually get all the goo off of the bellows and get it clean. So I just removed it mechanically, and it sort of worked, but it kind of had the same problem. In small samples and small tests, it worked fine, but when I actually tried to print, something like this that goes for 20 hours and has dozens of support layers, a few of them would always fail, and by the time I got to the end of the print, it was a mess. And you can kind of see how the edges of this are ragged, and there are some places in here where there are actually some holes that go all the way through the bellows. But yeah, this is not ideal. So I tried a whole bunch of different stuff, and what I ultimately came up with that worked the best was just PETG. So this is just ordinary Bambu Lab PETG HF, and this stuff just lays down beautifully on top of this material, and it sticks and you can still remove it. Now normally PETG would not be something I would think of in terms of putting it with TPU, because normally it sticks really well and be very difficult to release. But with this material, it lays down. You can see I've got a glassy smooth surface on the TPU. This laid down nice and smooth, 2 layers on top of that, and then it laid down the TPU on top of that and stuck, and it gave me a nice clean result. So PETG is the solution for support material for this particular stuff. And it's an odd combo, but it does work. The one other difficulty I had printing with this is that every once in a while I would get a little bit of a feed jam. And it's not really a jam. What it is resistance in the feed path, so that as the filament is being pulled through by the printer, if there's enough resistance, it can't quite get a grip on it. This stuff is kind of surprisingly slick. The extruder kind of loses its grip and can't pull it. And so I had some cases where I was pulling it through a bunch of tubing and adapters, and it would get to the point where it's like this, in this case, this is just the residual that's left on the support material. It would lay down, everything was fine, and then it would make kind of a thin spot because there was a little spot where the material wasn't pulling fast enough, and there'd be a little gap, and then it would pick up again. So it was really borderline. But once I got the feed path, ironed out and actually was running it through, bypassing the buffers like the H2D documentation recommends, I got much better results. And the resulting parts are very nice. These are only 0.4 millimeter thick walls, so 2.2 millimeter layers, but this is about as stiff as the 0.6 millimeter layers were with this, but to get the bellows to stretch the same distance, you can see the collapse length is actually shorter. So I think this will give a little bit more freedom for machine movement, and this stuff feels very, very tough to me. I think this stuff is going to work. This is the stuff I'm going to go with, and I've certainly got enough time invested in prototyping on this stuff. Every one of these prints took about 20 hours to print, so this was a couple of weeks of experimentation. But I think I got a couple of winners, and I think these are the ones we're going to use on the machine. Now, of course, the other half of this system is the bent metal parts, and I actually 3D printed prototypes of these just to make sure that they were all going to fit and that everything was going to be right before I actually ordered the parts from SendCutSend. Now, technically that's not true. I ordered the parts from SendCutSend, and then I thought, you know what, I'd better 3D print some of these and make sure they fit, and they did not, because I used the wrong STP files from an earlier version of the project, so I had to reorder a couple of them. But all of the correct parts are here now. So, I ordered these by uploading an STP file, so I already had the STP file. I might as well just 3D print it, and I should have done that, but I didn't. But these are the parts. These are 1.5 millimeter mild steel, laser cut. I've got some PEM nuts inserted into these that they did, and they did that and then powder coated them. And they turned out exactly the same as the 3D printed plastic parts, except of course stronger and prettier, and they fit just like the 3D printed prototypes do, or did. At least once I got the correct 3D printed prototypes. So we've got all the parts we need here to assemble these. Those go together. I can see that the holes line up, and we've even got the bent top bracket to attach to the Z slide, which is, I still continue to be impressed. I mean, I know I say it every time I get parts back, but I continue to be impressed with how good they look, and I continue to be impressed that I can just sketch something like this up on my computer and order it, and it just shows up in a week. Let's go put it on the machine, see how they work. Oh, and if I didn't say it earlier, SendCutSend is a sponsor of the channel, so they provided these parts for this project, and there is a link down in the video description for a discount if you want to give them a try. Okay, I've got the metal parts inserted, and I went ahead and put in some M5 button head screws, so this should just be ready to screw into place. It's, you know, a little bit awkward because the bellows are always trying to collapse onto the space where I'm trying to drive the screw, but let's see if we can make it happen anyway. And this is where we find out how good the 3D model was and if all of the threads are going to line up. Okay, and those ones do, and this oil line's a little bit in the way, but we're going to end up moving that when we deal with the oiling system. Would have been nice to have the screw holes out here where I could actually see the screws, but that's where they were on the machine. This is the Z bellows asymmetric, so I need to make sure it's going on in the right place, and I think I'm going to go ahead and just attach this first. Just so I'm not trying to work upside down against gravity with these screws. Whoops. It would appear that I have constructed some springs. Okay, I think that's that, and with it fully stretched, there's still a little side-to-side movement, so the collapse hasn't completely pinched onto the column. Let's power it up and give it a try. Okay, I've got the machine powered up and homed, and we should be able to move it around now. X-axis. Let's check out Y. Looks like the bellows are tracking fine. And that looks like about the maximum travel before we would actually hit the Z bellow structure. That's 212 millimeters of travel. From the front all the way to the back. Okay, what about Z? Okay, that seems to be tracking and stretching okay. And I just discovered something I had not realized. This bracket is colliding with the wider part of the column here. That was an oversight. Now, if I had actually put the 3D printed part on the machine and actually run it down there, I would have discovered that before ordering the sheet metal, but I did not. So let me bend that out so it won't scrape up the paint. And that's as far down as we need to go. Bellows are still loose. Well, the travels are all there. At least they will be once I do something about this bracket so it doesn't hit the column. The reason I've got this return on the side here is to give some anchor points for some cables and for a mist coolant system. So I do need that bracket there, but I definitely can make some changes to it to make it clear the column. That was just a dumb oversight, and it's something that I will have to take care of. Are these way covers going to work? Well, obviously they work. The question is whether they will last. And I'm actually optimistic about that. After playing with this material and handling it, it seems very resilient. It seems pretty cut resistant. I'm hopeful. I guess time will tell. And honestly, if after a year or two these things are worn out and I have to 3D print another set, that doesn't really seem like a big deal to me. I do feel a little bit embarrassed that I did not learn my lesson the first time and had to learn it again. 3D print the prototypes and test fit them before you order parts. It'll be interesting to see if I learn that lesson moving forward. I guess you'll just have to keep following the project and find out. A big thank you to Functional Print Friday for the idea to 3D print these bellows. I never would have thought of that. I never would have even considered it, but I think these turned out pretty well. So I'm thankful for the inspiration. Definitely go check out his video if you're interested. If you enjoyed this video, give it a thumbs up, feel free to subscribe, and maybe think about supporting the channel over on Patreon. Patrons can download files for all of my projects, including this one. Thank you for watching.